So my name is Professor Mauro Ferreira. I'm introducing myself because in case we have people from outside, I believe that we have a few students coming from outside. Is that right? Sure. Can you? There we go. You're more than welcome to Trinity College. So my name is Mauro Ferreira, as I said, and I'm Director of Teaching and Learning at Postgraduate. And the purpose of these meetings is to tell you about postgraduate opportunities in the School of Physics, right? So let's get started. And my apologies, because on my screen this looks much bigger than it does now. And now that you are in your final year, a question that will be asked time and time again, I'm afraid, is this: what are your plans for after you finish college, right? And my experience tells me there are three different categories of answers to this question. Category number one is, don't know yet, right? With some variation. There's another variation that's very common. I do know, but I don't want to talk about it. That's the other one. And the third variation, which goes like, sorry, me speak no English. It's just like any way to avoid the answer, right? So, and then there is, of course, category number two. It says, I'm ready to go into the job market, and I'm ready to, start working for whatever, whatever field or company or whatever. Right. And then there is a third, which is, I would love to do a postgrad course. And I guess that maybe most of you are considering that. If maybe you're still deciding, you're here just to see what the options are. And that's the purpose of today's meeting. If you're interested in that third category, I should also tell you that there are a few things to consider. Of course, if you want to pursue postgrad course, there are by and large three options. One is, of course, the financial aspect of it is a major issue. And then option number one, or something that you can do, is to fund yourself. And that can be quite expensive, but certainly possible. And then, if you're not going to do that, there are a few other options. First of all, there's the IRC scholarship, which is the Irish Research Council scholarship, and I'm going to tell you a little bit about that. And of course, there's another very common possibility, which is you approach a PI, principal investigator, i.e. Academic staff here, who has available projects and therefore might have some funding available, right? So these are the two common options. And I think, so that's why I think this meeting is important, because I'm going to tell you a little bit about this. And you will be, we're going to show you a few projects that are available. Sometimes we are not showing projects, we are showing the area, one area of work of a given researcher. So if you like that, you could then explore that a little bit further, right? And I'm sure you're thinking, isn't that a bit early in the year? This is what, week 2 or week 3 is a little bit early. And my point is, well, it's never too early to start thinking about postgrad opportunities, right? And you'll see in a second why this is indeed the case. Right, so I'm going to focus now on the IRC, the Government of Ireland Postgrad Scholarship, which is the IRC Program 2019. Okay? In case you don't really know what this program consists of, it's a program that offers scholarships for suitably qualified individuals, yourselves. Okay? Interested in pursuing research, master's or PhD. PhD is the vast majority of the funding is in PhD, in any discipline, etc., etc. Right? What does that entail? Well, that consists of a stipend to pay your salary, if you like, which is tax-free, of 16K per year, and of course that also covers the academic fees and also gives some kind of consumables or some for lab material or something. So there's an extra 2.5K-ish per annum. Right? So this is what this scholarship consists of. Now, of course, what are the criteria? The criteria, basically, there's a long application, the application form. I'm going to tell you a little bit more in a few minutes, but it's a bit of a long process, and that the decision is based on, say, 40%, this is the criteria, right? So 40% of that comes from the applicant. You as the applicant will have to write a pretty strong personal statement saying why you want to do a postgrad degree, and why you are the right person for the job, etc., etc. Just like almost like a job application, right? But equally important is the project, right? If you come up with a great personal statement, but you have like a wishy-washy project, it's not going to work, right? So you really need a solid project, and that's why we're here. We are here to help you, because we can help you put a proposal together, with a nice, interesting, timely project. And of course, in addition to these 80%, we also have the training, career development, and the environment. By that I mean you have to show that there is actually a career plan for you in the long term, and also the environment, as in, are you in the right environment? Is the lab that you're working in suitable for you, etc. So that's where these the criteria consist of. And just to say that, it's a very competitive process, and my understanding is that last year the cutoff was about 87%, so you need 87%, to actually get funded. The school has a pretty good success rate. We had about 16 studentships offered to the School of Physics in the past 2 years, right? Right, so one important point to highlight is about the applicants, right? What do you need in order to do, to be able to be eligible, basically? Well, to be eligible, all you need is to do physics or to complete your undergrad degree. But in practice, this says, well, have a first class or upper second class honors bachelor's degree or equivalent degree. But again, in reality, we know from the past few years that most students, the vast majority of students who were awarded the IRC, they had a first at the time of the application. It doesn't mean that this is always the case, but certainly if you don't meet this description, this requirement, the chance to become a bit, not as favorable. It's not as favorable. So it's important to know that you stand a much better chance if you have a first at the time of the application. Now, I did say to you a moment ago that why are we doing this so early in the year? And the reason is right here. Because the deadline is just around the corner. It's about a month or so away from now. And so the call was open just a couple of 10 days or so ago, and the deadline for you as the applicant is 1st of November. And then there is a bit of time for the referee, for the supervisor to submit some extra material. But the bottom line is that this is a hard deadline, that there isn't really much we can do about that. So 1st of November, you have to have your application submitted by then, okay? So how to apply? Here, the details can be found right here. And I urge you, if you're interested to attempt that, to have a look. Go into the website, and you see, you see that the application form is quite long, and that's why you need time to put this together. Now, I want you to, I want you looking at me, because this is a very important piece of information I'm about to give you. Right? Because in the past, I remember students approaching me 12 hours before the deadline, right? So it's not going to work, right? So I'm warning you, if you are interested, by all means, put your act together, contact potential supervisors, and then you start working on your application. Because if you leave that to the last minute, it's not going to work. Is that clear? Great. Right, so, and that means how do you start? Oops, sorry, my mistake. So what do we start? Well, this is supposed to be much bigger here, but first step is to identify a project and a supervisor. And now what I'm going to do, what we are going to do, is we're going to give you a list of, a series of short presentations about available research projects. Is that okay? Now I want to address my colleagues, professors who are going to be these presentations. I just want to remind you that we have 17 speakers, right? And so I am going to be brutal in the timekeeping side of things. So I'll give you 3 minutes, right? So if I stand, that means your time's up. Please try to come to a conclusion as soon as you can. Because remember, 17 speakers, we want some time. So for information, what we're going to do in the first hour, we're going to give you these short presentations. And then in the second half, we're going to move upstairs where you have a bit of time and chance to talk to us about, some of the specific details of projects, etc. Is that clear? Okay, so let's get started. And I'm going to be the first, of course, because So I'm going to start here by going into neuromorphic computing. As a project that I'm offering, if you're interested, what is neuromorphic computing? Well, it's a field of study that aims to imitate nature and design brain-like machines that can process, store, and transmit information with minimal, very, very minimal energy expenditure, right? And one way to do that is to use nanowire networks. You can see here like an image of a brain or a real brain or a neural network, and here you can actually see these nanowire networks. Just you can see some resemblance, of course, and in fact, these materials function very much like, have some of the functionality of brains, right? But there's one big problem. The big problem is this. We know that our brains, they activate small parts of their cells depending on the task. If you're eating, only a small part is activated, etc., etc. However, these networks, unfortunately, when you try to pass information through them or current, they light up like entirely. So it's as if rather than using just a small fraction of the wires, you kind of use them all, which is very energy inefficient, right? Thankfully, just actually a couple of weeks ago, a paper that I published with collaborators on Nature Communications, we actually came up with a pretty interesting idea. We actually identified a set of conditions that determine when networks highlight only a small fraction of them. Rather than activating the entire network, we know the conditions under which the network will self-select a tiny fraction. And this is really interesting because then we have now the knowledge, the required knowledge, to maybe make these materials function as artificial brains or synthetic brains, if you like, right? However, of course, this paper was done, everything was done on a macroscopic scale. There's still a lot to be learned about what happens microscopically or atomistically. And that's when the challenge begins. So if you're interested in pursuing this, in other words, trying to understand this from a microscopic or atomistic point of view, this project might be suitable for you. If you have a solid background in quantum mechanics and condensed matter theory, if you like challenging problems, if you're interested in machine learning type of activities, or if you want to work in the exciting area of neuromorphics, this might be for you. And finally, just to say, the funding is actually already available, and that is important to highlight. I have one more project here, but I'm not going to talk about, but you will have a copy of that if you are interested in. Okay, so I'm going to, by the way, you will get a copy of all these presentations at the end. And again, my colleagues, I should inform you that we are being recorded, right? So everything here is going to be sent to the students. And remember, we have students who are abroad right now, so everything's being recorded and it will be sent to them as well. Right, now I'm going to move on to, I'm going to skip Louise's. Louise asked to go a little bit later. So just bear with me for 1 second, because Johnny Coleman asked me to speak on his behalf. So my 3 minutes are up, right, of course. So now I can only use 30 seconds for Johnny. Okay, here is, I think Johnny needs no introduction. Johnny Coleman needs no introduction. And then, of course, he's joined from the School of Physics and Number. And basically, in a massive lectures here, what they do is they make 2D materials for applications in energy storage, printed electronics, and sensing. And they have some quite amazing systems and applications that they've been working with. And actually, one way to see that is just look why work for me. And then you have 1, 2, 3, 4, 5, 6, 7, 8, 9 natures and sciences over the past, I think, 5 years or something, which is really quite impressive. So that's all that Johnny sent me, so I don't really need to expand on that. Right? Okay, so Paul here? No, Paul is not here, so I'm going to move on. Brian, here we go. So remember, 3 minutes each. 3 minutes, and your time is up. Thank you.
All right. Hello, you all know me by now. It's very hard to compress something in a short period of time, but just hopefully to introduce the topic, as I say, we can talk later. So what I'm working on and what is just first past the entrance in with the Sustainable Energy Authority of Ireland, we got funding for a postdoc to work on this, so we start momentum, is to look at light pollution in Ireland. You see here an image looking up the coast and a zoom in on Dublin. And it provides basically an untapped resource, certainly in the Irish case, and there's only basically one other group I know of in the world working on this sort of stuff, where we're taking the images that Hadfield and so on took from space. Georeferencing them is a known issue. Intensity calibrating them is a bit more tricky, but the new digital cameras are extremely sensitive. For instance, I can actually pick out Christmas lighting decorations at the Dundrum Town Centre on individual lampposts. So it gives you a great tool to actually see where light is being emitted. Why is that important? Well, the light tracks the energy use. So it's a way of actually looking at the energy use, and we could get that information on a night-to-night basis. Instead of waiting for a census every 5 years, we could actually see how the population is shifting around the country. We could see the growth of industry and whatever on a nightly timescale, because you don't use the energy unless it's a fraction of the amount of money you're generating locally and where the population is. It tracks very well with the population. If you want to put in a nuclear missile site or something, you'll probably put in security lighting, and North Korea really stands out in that respect. Okay. But in the case, the driver of this is that in the case of Ireland, for instance, it's gone off the edge, but the amount of light emitted by the Republic of Ireland went up about 80% over the period of the Celtic Tiger, and it doesn't go down. So it's a handle to get a use on our energy usage, where it's being used, is it being wasted, what type of energy is being generated, is it commercial, and this is mainly public lighting you see here. You can see the center of the city, amazing amount of energy, which makes the sky glow at about 1,400 times the natural level when it's overcast. You see color, even if you take a snapshot on your smartphone. So what we can do is actually use these imaging products and produce data from these, and also nightly calibrated data done by dedicated satellites. So this is taken from 400 kilometers, gives us resolution down to less than 10 meters. From 800 kilometers, you get about 750. But we can see detail in the countryside and compare it with other locations, the UK, for instance. And we can tie it in. We can actually map out. Here's a Korean data set. We can map out land use. We can map out where the public lighting and so on is. And we can estimate currently the cost, about 2.5 million, roughly, spent in light going into space. So at the moment, as I said, is myself, we'll be getting a postdoc started shortly. We'll use the combination of this digital imagery and the satellite data. We can calibrate this if you're interested. If you've done any work with astro imaging, we can use the stars that are in the corner of the images to check the intensity, the calibration between the intensity and the counts in the image. And we can generate then products that are usable by other departments and areas that can be used then for developing dark sky tourism and so on. So there are a number of spin-off products, but primarily this project is to generate the calibrated data sets. All right, thank you.
Thanks,
David, you're next.
Hello everyone, my name is Owen McCarthy and I'm going to present on behalf of Professor Lewis Jones, who's away at the moment. So we're from the Advanced Microscopy Laboratory and we're the most advanced electron microscopy facility in the country. And we are based in the Trinity Technology and Enterprise campus, which is about a 10-minute walk from the main Trinity campus. So essentially what we do is we take high-energy electron and ion beams of various different kinds and we analyse materials and change the properties of materials using these beams. Excuse me. So our research portfolio is quite diverse. We study the fundamental properties of materials, but more than that, we look at 3D printed materials, characterise them, and we also look at medical devices and the pharma industry as well. So what type of projects are available in the AML? So if you really want to be a hardcore experimentalist, you might be interested in atomic resolution imaging, for fingerprinting and hydrogen fuel cells with catalysis. If you take a more engineering approach, you might be interested in designing new type of electron microscope hardware components. Maybe you'd be interested in astrophysics and studying the structural and chemical composition of micrometeorites. If you're into kind of program side of things or more theoretical calculations, there's big data projects, machine learning for image informatics, and in data mining. These are atomic resolution images that have been altered and theoretically put together. Or if you're interested in 3D printing, there's a manufacturing structural analysis of new 3D printed parts. If you have any interest, I want to find out any more information on these projects, you can contact me, which is I'm Owen McCarthy, or the supervisor is going to be Lewis Jones. So contact Lewis. Any questions, I'll be around afterwards upstairs. So I'll answer any questions on those projects.
Great, thank you. That's the way I like it, 1.5 minutes. That's the way to do it. Charles, I just want to say. Right here.
Okay, thanks, Mauro. So my research is computational, it's many-body quantum mechanics, and there are a lot of opportunities for code development, including writing code in C and using things like message passing interface for parallel programming. So physics is many-body effects in the light-matter interaction. What I have been working on for the last number of years is semiconductor surfaces and interfaces. If my 3 minutes don't run out, I'll show you an example of that. But the area that I'm moving into at the moment is biomolecules. So what you see here is a light harvesting complex from a purple bacterium. So this little thing that looks like a jet engine, that's the whole thing. This is the protein scaffolding. And this is the array of chromophores that actually absorb the light. And the whole thing is all of the chromophores are coupled together, they interact, and the whole thing behaves like a miniature antenna. So each one of these tails is a chromophore, and 16 of them in this arrangement. That's what one of them looks like. It's a bacterial chlorophyll molecule. And using these many-body methods, so far we're able to predict the absorption spectrum really pretty accurately. Okay, these are the two peaks of the absorption spectrum of a bacterial chlorophyll molecule that absorb light from the sun. So that's the application. What's the physics in that? Well, what we're in this particular problem, we're interested in how light gets absorbed by the light harvesting complex, and then how the energy from that is actually funneled into the reaction center where it drives a water splitting reaction. A lot of people these days are trying to do that artificially. So that's where two water molecules combine, you get 4 protons an oxygen molecule, and electrons. Nature does that very efficiently, and so how does that actually happen? Well, the plan is to build a pairwise model of interacting chromophores, and to use this, they can solve Peter equation from many-body quantum mechanics, so that's Green's functions, Feynman diagrams, that kind of thing. Put it all into a high-performance computer, solve the equation, and then not only look at the absorption of a single molecule, but of this entire complex, and also we need to include the effects of the protein background on the absorption as well. So quite a complex problem. So that's a new project. This is just an example of what we were doing previously on semiconductor surfaces, able to reproduce the effect of an interface between gallium phosphide and silicon on the reflectivity. Okay, so stop there. Thank you.
Thank you, Tom. Dave, you're next. Is that the better one?
Yeah, it's out there. Just want to be up here. Okay, so Dave McCluskey is my name. I'm in the School of Physics. So basically, my interest is the interaction of light and matter, particularly on small scales, microscale, nanoscale. So in the past, we've done stuff with light scattering from dielectric objects, integrated optics, plasmonics. We used helium-ion beams to implant nitrogen centers into a diamond, do some quantum optics with that. Lately, we're doing a lot of stuff with optics of 2D materials, and also heating and understanding temperature rise and heat flow in nanoscale systems using optics. So I have two ideas for projects that I'd like to pursue, and I'll just present them here. They're very optics-based ones today. So the first one is based on electrically controllable phase shift on reflection from 2D nanomaterials. So there's a lot of work been done on this very recently, where they've shown that the refractive index of these 2D nanomaterials can be tuned very effectively with an electrical gate. So WS2, for example, has a very high real index and a reasonable imaginary component. And so basically, by just applying an electric field across this, you can change the reflectivity from this thing. And so why would you want to do that? Well, you can create ultra-fast modulators for sending information for basically communications. We're interested in, we did a quick calculation with transformative code and realized that, we can actually tune the phase shift on reflection. And that allows you to do some other things. You can interfere this and get a much higher signal-to-noise ratio in your communication. But you can also do real-time holography or stuff like this. So normally holography is limited by, they use spatial light modulators to do this, and it's limited to a few hundred kilohertz due to how long it takes this liquid crystal to relax. We think we can do this in gigahertz range, so we'd like to do that. Well, obviously you're not going to make a display out of that, mostly for communications purposes. Okay, so that's the first project. Basically, this is based on some nice physics of trion generation through charge injection and shifting of the reflectivity. Okay, so the second project is also, so if you want to, there's some papers here, nanoletters last year, and you'll develop all these skills here, chemical deposition, optical characterization, electrical characterization, doing this. So we'll be collaborating with maybe Niall McAvoy's group in chemistry with this. Okay, so second project, same thing, different wavelength range. So we're doing a lot of 3D printing at the minute. We do ceramic 3D printing, and we do metal 3D printing. I brought along some little things here. I wish I could hand them out, but we haven't measured all of them yet. I'll give you an idea of how these things look. And basically, these are done in 3 different material systems, 3 different printers. This thing here is a metallic. This is a cobalt chromium. And basically, this little hole here will transmit light at about 3 gigahertz. So we're looking at making fully integrated devices for satellite communications in this sort of 3 to 30 gigahertz range using metal 3D printing. This is in collaboration with Nokia, Bell Labs. This ceramic material here, they're quite interested in this as well. So this is for dielectric resonators and for dielectric antenna in the 60 gigahertz range. And this here is also 60 gigahertz. So the idea is that for your 5G communication, that you'd have an array of antenna on the back of this, and you'd be basically doing what's called spatial division multiplexing. But see, I'm running out of time. So with this project, there's a postdoc working on this. There's some prototypes. You'd be printing here, and then you'd be going into Nokia Bell Labs in Blanchardstown, some industry interaction and measuring in their anechoic chambers. And we already have sort of specs and designs for more complicated things for you guys to do if you were to take on this project. So do just, I'm not sure if I'll be here at 4, I have another thing to do, but do feel free to give me an email or a call into the office or that if you're interested in either optics in the visible range or in the RF range. So.
Thank you. Oh, yeah. Next one. That's the next one. So.
Okay, so my name is Professor Cormac McGuinness. So I'm here to talk to you about 2 potential projects. My interest is in surface science, the growth of nanostructures and surfaces, and their characterization most often by spectroscopy, optical spectroscopy, as well as X-ray spectroscopy, which in particular is my specialty. However, what we're developing here is a novel self-assembly process, or rather a self-assembly process to develop a novel nanostructure which we've demonstrated already on the surface. But what we want to be able to do is we want to be able to take what we've demonstrated on the surface here, where we're incorporating a porphyrin molecule in the middle of a graphene nanoribbon. And what we want to do is we want to be able to build a device based upon a porphyrin in a graphene nanoribbon in a field effect transistor device. And so that in the future, what we could have is somebody could have a breath assay, and so the exhaled breath could we detect volatile organic compounds, which could react in a single molecule sensitive detector here, or sensor, nanosensor here, such that we can identify what these volatile organic compounds are. And so if we could identify nitrites, that's indication of lung irritation, such as you might get from asthma. But if we can fingerprint many different volatile organic compounds via a whole range of different porphyrins, and the porphyrins are typically metal porphyrins, such as this one here, where we can have either zinc or magnesium or copper or cobalt or nickel in the center. In fact, Charles Patterson's project showed, for the chromophore that he was showing a porphyrin, and porphyrins are present throughout life. Iron porphyrin is the center of heme or hemoglobin. Magnesium porphyrin and zinc porphyrins you'll find in chlorophyll, etc. So what we do? One example of what we do is we might take small molecules like this one here, and we could throw lots of these on a surface along with a porphyrin like this, and these can self-assemble into chains. So we can have chains of, as we heat the surface up, we can establish a polymer chain like this. As we heat it further, we end up with a nanoribbon here, which then incorporates the porphyrin. Okay. So an example which we have here, which we've demonstrated, is here. This is the actual porphyrin in the middle of our nanoribbon. So what's next? Here are some other STM images of these porphyrin networks. So porphyrin networks are connected by these graphene nanoribbon wires, and so we can either do them on surfaces such as Goldman-1, which is very flat, and we can get these kind of networks going in all sorts of directions, or we can do these on a stepped surface. So here we have parallel nanoribbons incorporating these porphyrins. What we need to do is we need to take these off. We can characterize them in situ via X-ray photoemission and by scanning tunneling microscopy. But ultimately, we need to take the graphene nanoribbons off, and there's chemical ways in which we can do that. We can delaminate, get the layer of the networks of porphyrins in the graphene nanoribbons off, transfer it onto a silicon dioxide surface, and then we can sense small molecules as they react with a porphyrin. So ultimately, we're trying to build an electronic nose, but there's a lot of basic research which is going on. Now, there's other more standard surface science things which I'd like to also explore. And so this is an example of iron nanowires that we would like to create on a stepped platinum surface. We cap it with gold. And then what we do is we use some X-ray spectroscopy at synchrotron facilities such as BESI in Berlin or the Advanced Light Source. And we would measure the X-ray spectroscopy and understand the magnetic behavior of these atomically thin and few atom wide iron nanowires. Okay, so if you'd like to talk to me about either of these 2 projects, then you can see me upstairs afterwards.
Thank you.
Matthias, you're next.
So hello, my name is Matthias Möbius. So I'm experimental soft matter physicist. Yeah, so soft matter is basically soft stuff, gooey stuff. Yeah, and I currently have 2 PhD positions, actually fully funded PhD positions open. Yeah. So my field of work is essentially the rheology of complex fluid. So what does that mean? Rheology means flow behavior, how things flow. Yeah, and complex fluids. Well, they're fluids that are not quite liquid, but also not quite solid. They're in between. Yeah? So examples are, for example, shaving cream. Yeah? If you put shaving cream on your hand, I'm not going to do this because it's a mess, yeah? But it will not flow through your fingers like water does. Yeah? And you can wait for a few minutes, it will not flow. Yeah? However, if you force it externally, it does flow. Yeah? So it has both sort of solid type behavior, but also liquid type behavior. Or ketchup, yeah, which is basically water, vinegar with some tomato cells. Yeah? I mean, you may have noticed that it's very hard to get it out of the tube, yeah, because at that point it has a high viscosity. However, once you force it externally, the viscosity actually drops quite a bit, yeah. And then you drain your French fries with a ketchup. Yeah. So complex fluids, they not have one viscosity, but basically the viscosity depends on the external forcing, and that's one of the hallmarks of complex fluids. Yeah? Unlike water or alcohol, which have a constant viscosity, which maybe changes with temperature, but not with the forcing. Now, currently, I'm studying nanosheet suspensions. Yeah, you may have heard of graphene. That's the most famous example, but there are many others. And what people like to do is sort of this printed electronics to print this stuff on substrates, yeah, and make circuits. Yeah, and inkjet printing is cheap. Now the problem is, in order to do this, you need to understand the fluid dynamics. Yeah. So for example, typically inkjet printing, you force it through some 20, 30 micron nozzle, and you get the so-called jetting, and then it splashes on the substrate. And in this case, for example, you can see you get sort of this corona, and little droplets are emerging, and that of course affects the resolution of your printed features. This doesn't typically happen on paper, yeah, because it's porous and it sucks up the liquid, but on hard substrates that are used for this type of application, you can get that. Yeah? And that depends on all sorts of things like surface tension and viscosity. Yeah? And it's more or less understood for normal liquids like water and other alcohol. But for these nanosuspensions, they're complex fluids. Yeah? The viscosity is not constant, also the surface tension. And so the first project is basically to use high-speed imaging to study this jetting behavior and the splashing behavior and how this depends on concentration. And the second project is basically on how these things dry and what structures they form. Okay? So if you have any questions, just email me or we can talk after the session. Okay, thanks.
Thank you.
Hi, I'm Stephen Carr, and I've just moved to Trinity with funding from the IRC. We'll talk about a little bit what we'll be doing in my group, which looks at quantum transport in two-dimensional systems. So what we do is a theoretical group, so we use theoretical and computational methods to study two-dimensional materials such as graphene and heterostructures that are made from different materials stacked or put together in layers in different ways. So as well as electronic properties, we're interested in more exotic properties related to the magnetic moments of electrons and other degrees of freedom with fancy names like Valley or pseudospin that arise when you put electrons into a two-dimensional lattice. So we have two main motivations. The first one is to predict new systems that allow us to manipulate these properties so that they can be detected in future experiments and form the basis of future devices. Our second motivation is to simulate realistic experimental conditions where such systems are currently being measured. So to move away from the very, very perfect system, where we have a single incoming electron wave, and to consider experimental devices where we have a messy system with defects and a lot of different contacts, and to see if the signals that are measured actually represent the underlying fundamental physics. So the methods we use span a wide range. We start analytics that can be done in pen and paper using the Dirac model for 2D materials, and we scale all the way up to quantum transport simulations containing millions of atoms that accurately represent the actual experimental length scale that these things are measured at. We also want to move into using machine learning and genetic algorithm techniques to aid in the design of this type of structures. So two possible projects that I would look for people to apply to the IRC with. The first one involves what happens when you have two layers of graphene stacked on top of each other and give them a twist. This was a very esoteric topic until recently, and this summer there have been 3 or 4 Nature and Science papers showing that this can be done in a controlled manner and at a range of unexpected and interesting phenomena, including perhaps superconductivity arise. But there's still a lot of open questions. What happens if this system isn't perfect? What happens if we add additional electrical magnetic fields? How can we interplay with this? Or if we couple the system to an additional layer, can we control it further? Another possible project is to look at the effect of strain. So strain, when you stretch something, you might be aware of in usual materials, but in two-dimensional materials, an unusual effect happens where the electrons act as if they're experiencing colossal effective magnetic fields of the orders of hundreds of Tesla, so far greater than can be achieved in a lab. With real magnetic fields of different signs, this can be used to control electron flow using these so-called snake states. So instead of the Lorentz effect where electrons move in circles, you can direct them along a path by changing the sign of the magnetic field. We want to see can we cause something similar by carefully designing a patterned strain so that the underlying pseudomagnetic field can induce a similar effect. So if you're interested in this type of project or something similar with two-dimensional materials using theoretical or computational methods, I'll be upstairs and my office is in the Lloyd building if you want to come and talk to me about it. Thank you.
Which one do you want to present first? Okay, so Stephanos is already here. Okay. Yours is on the desk. Right. You just go.
Okay.
Right.
Yeah.
It's like cafe.
Okay.
Actually, the cafe.
Okay.
Right?
Yep.
Right. Stephanos
just
right there.
Okay, I'm actually going to give a description first of projects that are available in the group of Stephanos and Vito. He can't be here today because he's at a conference, but he'll be back tomorrow. So if anyone wants to contact him, his email address is there. You can call to his office and he'll be more than happy to talk to you. So Stefano runs quite a big computational physics group, computational spintronics. They work in quite a lot of areas, so materials, design, electronics or spintronics, but the projects that he wants me to talk to you today about are in the area of machine learning. So machine learning identifies patterns in data and then reacts to that data. So the idea is you generate or you have access to a huge data set that can be described by a bunch of different descriptors, such as like the number of atoms or the type of atoms, the valence of those atoms or their mass or some magnetic properties, and you develop an algorithm that can, well, combine all of this information together and output some particular property of that material. So for instance, if it's magnetic or its crystal structure or something like that. So machine learning is used a lot already in data science, so they use it in risk assessment, and in the last few years it started to move more and more into material science. But one example is you can use machine learning to teach a car how to drive. So for instance, you can train it on a data set of what a pedestrian crossing looks like or a zebra crossing, so that when that car then goes out into the wild on its own, it can recognize if there's pedestrians crossing and brake appropriately. So Stefano here asked me to talk about two particular projects that you can contact him about. One is related to materials discovery. So if you look at the periodic table, there are billions of different ways of combining all the various elements. And if you're looking for one particular material or a group of materials that can do something, so that is ferromagnetic, for instance, you don't know where to begin with all of these combinations that you can have. But you can use machine learning to develop an algorithm to sort through all of this data and generate it. So Stefano was involved in a collaboration recently where they found new types of magnetic materials. And then the second project he wants to talk about is using machine learning for many-body problems. So these are very complex problems that very quickly get impossible to solve computationally. So the more and more atoms you include, the more and more electrons, it increases exponentially and you cannot solve it. So Stefano wants to bypass this problem in a way by using machine learning to dig through all of this data and extract the relevant physics. Yeah, okay, so you can talk to Stefano and he'll be back tomorrow and his email address is there. Okay, so that's Stefano's project, and then I also will be happy to support someone applying to the IRC. So it's this one. Yeah, so I joined the physics department here in physics about 2 years ago, and I also run a computational materials group where I'm looking in particular at finding materials for energy applications. So what do we do in my group? We look primarily at layered materials that were spoken about earlier. So these are stacks, materials that are very tightly bound in plane, and then they're layered on top of one another, almost like, say, a deck of cards. So in between the different layers, you can fit other atoms or molecules. And so, for instance, this is how a battery works. So rechargeable batteries have these layers of materials within which, say, lithium ions can move in and out of. So lithium-ion batteries are currently the most popular rechargeable battery. And the way they work is these blue atoms are lithium atoms, and as you charge and discharge your battery, the lithium atoms move from the anode to the cathode, and electrons then move in the external circuit that you use to power your device. But lithium batteries, they're basically as good as they're going to get, which isn't great. Also, lithium is expensive. You have to dig it out of the ground. It's quite dangerous. Lithium metal is dangerous. And lithium is, in its ion form, is lithium 1+, so it has only 1 electron redox capability. So we can do better than this, and the project I'm interested in is going beyond lithium to multivalent ions, such as aluminium, which now has 3+. So the energy density that you could get from a battery made of aluminium is way higher. The problem becomes in that a lithium-ion battery, the anode here is primarily made of graphite, but the lithium ion is quite small, the aluminium atom is much bigger, and it simply just won't fit in between the layers. So I want to find or search for an electrode material that can host aluminium-ion batteries, or aluminium ions, or other types of multivalent ions. So the material I'm particularly interested in is this new family of materials that are called Maxine materials. So the picture on the left there is an experimental picture of it. And we already know that the aluminium ions can fit in between the layers. So I want to use computational techniques to determine whether or not it's going to work well enough as a battery. So we can calculate, say, the diffusion of the aluminium in between the layers. We can calculate the voltage of the battery and its specific capacity. And some of this work then can be done in collaboration with an experimental collaborator that's in the US who produced that picture on the left. Okay, so I'll be upstairs afterwards if you have any questions about this or any other project. Thanks.
That was quick. Thanks. So, hi everyone. My name is John Gould. I'm actually relatively new to the department. I arrived only in the last year. I'm a theoretical physicist, and my topic of research is basically on what I would call thermodynamics of quantum technologies, or quantum thermodynamics. So basically, currently, I've spent my last few months building up my group. It's basically me, 3 postdoctoral researchers, 3 PhD students, and 1 part-time administrator, but there's always room for 1 more if someone wants to apply for external funding. Okay, so essentially what do I do? Well, I mean, if you think about what thermodynamics is, it's quite interesting that the reason why thermodynamics was invented was because of industrial revolution in the 19th century. You know, if you fast forward many years later, you see that now there's no doubt but the 21st century is essentially the information age. So we're miniaturizing devices essentially to process information. And my research is basically inspired by that. So the questions I ask, and which could be the basis of an external application for funding, are, for instance, if you think about what are the smallest possible engine cycles, in other words, can you convert heat currents into work currents, and ask questions like, if I have such a small engine, then how can I maximize its efficiency while not maximize its power without compromising the efficiency? And then I'm also interested in a concept which I call quantum batteries, which is absolutely nothing got to do with a real battery, but rather a fundamental question. So if I have a many-body system comprising of many interacting particles, then if I ask if I pump energy into that system, what are the fundamental microscopic properties which makes that unit a good energy storage device? And I guess a third topic which I'm currently interested in is what I would call more fundamental, maybe more suited to a non-computational physicist, which is, you know, given that in quantum systems comprising of many different components are intrinsically complex, and thermodynamics is essentially a theory which makes things simple, then how does this essentially complexity to simpleness trade-off evolve as I make the system larger? Okay, so what is the relationship between thermodynamic emergence and quantum correlations? And finally, I'm also interested in generic transport scenarios, heat and particle currents through disordered networks. So if you want to talk to me about any of that, just give me a shout. Thanks.
Yep. So you just need to close there. Is that the one? No, yep. That's the PDF. Do you want the PDF? Yeah. Okay. Hi guys, my name is David. I work in condensed matter theory, and my objective really is to push forward what we can do with simulations of materials of molecular systems based on quantum mechanics, more specifically density functional theory, which is one of the most popular methods used throughout the physical sciences really for simulating materials. So I'm happy to develop projects that are really abstract, so pen and paper projects with a bit of visualization using Mathematica. We can do coding projects, so if you're into the computer science side but want to make a connection to physics, then I'm happy to develop one of those. Or we can just do purely applied projects. We can use one of the tools that we've developed in my group in the last couple of years, take it down off the shelf and apply it to the sort of system that you're interested in. Okay, so I'm fairly agnostic as to the choice of system. Okay, if contemporary theory does a rubbish job for it, I'll be interested in that system. Or if there is no theory currently for a given effect, then I'll be probably interested in that system. Okay. Now, personally, if I have to apply my theory, I like to wake up in the morning and feel I'm doing some unambiguous good. So I feel a sort of personal obligation to look at green energy problems. Okay, because there is a mounting sense of urgency at the moment. So I'll give you 2 examples here of physical effects that are unexplained, basically, which are very relevant to green energy. So the first is in the context of high power density rechargeable batteries. Okay, so not the lithium-ion batteries in your phone, but the one in your parents' Tesla car, if you're lucky enough, right? So you're driving a lot of power up quite fast. Okay, so there, as Nuala said, you have ions that move from a cathode to an anode, depending on whether you're charging or discharging. Okay, and I'm interested in the cathode materials because they're strongly correlated materials. Often they're oxides. They're in the same family of materials that give you high temperature superconductors. Okay. So the most common high power guys are these lithium iron phosphate batteries. Okay. So normally when you do a DFT calculation, you look at the fully charged state and the fully discharged state. Okay. When all the layers are full of lithium,
or when they're all empty, and you take the total energy of the two states, you take a difference, you can at least calculate the voltage of the battery. Okay? Now I know about your phone or your car, but mine spends all its time somewhere in between, fully charged and fully empty. Okay? So that's important. You want to know how easy it is to get lithium ions in and out of the cathode material when you're at some partially charged state. And you want to know the voltage there. Okay? Because if the voltage gets too high, you have some kind of catastrophic breakdown, your Qantas jet catches fire or whatever. So you need to know this, right? Now, if you have a predictive theory of how this works, then maybe you can get, if you have a descriptive theory, then maybe you can get predictive. Maybe you can start to alloy with something other than iron and get the properties that you want. So in this context, there is an unexplained effect called staging. So when this thing is half charged, where you find this every second layer for the lithium ions is empty. No one knows why it prefers to have this wave-like pattern in the lithiation. And as a result of it, you get charge density waves and spin density waves. Okay? And when you look at your leaving cert chemistry, A-level chemistry, what you find in this half-charged state is every second iron atom, shown by blue and yellow here, is 2+ or 3+. Okay? But the state is degenerate. Okay? So there's no reason for one iron atom to be 3+ and the other to be 2+. So this, by construction, is a multi-state determinant wave function here. So every grain of this material is like a Schrodinger's cat box. Okay? And when you make a measurement, you find a half there is a 2+ and a half there is a 3+. Density function theory does a terrible job with those multi-state determinant problems. We've developed a lot of theory over the last couple of years to try and patch up the theory and make it predictive for those types of states. So that's batteries, that's storage. Now power generation. There's an effect called signal fission, which can be used to beat the quantum speed limit, the Shockley-Kweisser limit on solar cell active layers. The best solar cell that works with just creating electron-hole pairs from photons can get you to 37% efficiency, and you can't go higher. So you need to go to exotic quantum effects, like a single electron-hole pair splitting into two electron-hole pairs with opposite spin. That's triplet fission. And the triplet states are protected, and you can drag them out to the battery. Okay, so we've developed a lot of methodology there in recent years, and we'd like to deploy it now. Okay, so thank you very much.
Hi, for those of you who don't know me, my name is Louise Bradley, and I lead a group working in the area of nanophotonics. So just to give you an idea of the size of the group, we're usually between 6 and 8 people working in the group at any given time, and there's usually quite an eclectic mix of people from different parts of the world. So we have nice time between people from China, Romania, sometimes the US, France, Germany, Ireland, and so on. So at the moment, these are the team members, and we have our funding from the IPIC Centre, which is an SFI-funded centre in Cork dedicated to photonics. We're funded directly through Science Foundation Ireland. I get funding from Tyndall, and also through the Irish Research Council, and that's why we're chatting with you today. So nanophotonics, I'm going to keep this really brief. I just want to give you a flavour so that then if you're interested, you can come and talk to me more. So I'm putting up 2 possible kind of project areas which are directly related to the kind of work we're doing at the moment. So nanophotonics is really about controlling light on the nanoscale. So that includes the emission of the light, the direction of the light, and the propagation of the light, and being able to do new things with light which we couldn't do before. So one of the ways that you can do this, you can confine light on the nanoscale using metallic particles and metallic nanoparticles. But once you've typically made the structure, then it's fixed. So what you want to be able to do is to create a smart structure or a responsive structure or a dynamic structure, one which you can change the properties of. So for example, you could select to have light emission enhanced at different wavelengths, or you could select to have the light guided on the nanoscale in different directions, or coupling to different kinds of waveguides, or going into different kinds of information processing or switching type behavior. So we need to think about ways to make these systems dynamically responsive. So just to give you a flavor of what we do, so we do the simulation of the structures using finite difference time domain theory or using finite element theory. So for people who are interested in simulation, we have projects that are suited to you. We do the fabrication using things like E-beam lithography, but we also use chemical synthesis techniques to fabricate tiny metallic structures with particular properties. We use nanoscale emitters such as quantum dots, which we source from people in chemistry, or we use 2D materials. And so here's an example of a 2D material which we've characterized in our lab, which has come from Niall McAvoy over in chemistry. And this material is a monolayer of WSE2, tungsten diselenide, and we have, so this is what you can see in a bright field microscope, but we've developed tools in our lab to be able to look at the dark field image, and the dark field image means that you see the light which is scattered from the object. So you illuminate it, you don't detect any of the illumination light as you do in bright field, but you just see light which is scattered. And so you can see that you have a lot more information on the structure, and you can then take spectra at any given point. So these flakes are just 100 nanometers thick, and they can be, in some of the dots we're looking at, they're only a couple of nanometers big, and we can take the whole spectrum and look at different points. So we use these 2D materials, and we use vanadium dioxide, which is a phase change material. It changes from semiconductor to metallic under different conditions to be able to make these plasmonic structures, so these nano antennae, to make them dynamically tunable. That's one kind of thing we work on. Now, one of the problems with metals is that they're lossy. So at the moment, they're the best option that there is, but the losses are a big drawback. So what can you do if you want to do nanoscale photonics with a less lossy material? So we start to think about nanophotonics using dielectrics. And so using that dark field microscope that I showed you earlier, these are lots of silicon nanoparticles, and you can see that if we look at it in the bright field microscope, it looks green. If we look at it in a dark field microscope, it looks red. So they have the properties to directionally scatter light of different colors in different directions. And again, we want to be able to see, if you couple this with something, can you make it into a dynamic resonator? So are you able to change the properties of emitters to change its relaxation pathways depending on how you actually control it? So we have all these custom-built tools for characterizing these nanoscale systems, which we make in the advanced microscopy laboratory, and then we characterize them in our group, and we collaborate with chemists, we collaborate with people in Ireland, in Germany, and in Hong Kong on different materials and growing them and coupling them together. So we take materials from anyone who will give them to us, and we put them all together. So we have lots of different kinds of projects going on, and these are just a flavor of the kind of tools and the kinds of things we do. So if you have any questions or any interest, I think the thing to do is to ask me later. Okay, thank you.